we'll just follow our argument here to write down this stuff. So you see, for the number sold, turns out to be equal to the max. Sorry, the minimum of those, right? So you have this times the minimum of D and S. That's the first part. That's the part you sold. And then you spend some money. That's $20 per piece. And the number of so the second one would be the number ordered, right? Number ordered. The number ordered, you know, is S, right? We used that, and then we have to look at the holding cost and that stuff. The holding cost turns out to be equal to 9 times the max of 0 and S minus D. So now we just need to simplify this. Not much we need to say here. It's a simple multiplication. Here, not much we need to do, but here we can simplify that. Let's just look at what is minimum of the D and the S. So what do you do with that? Well, now let's see. I'm looking at this part, the 15, let's take a note of this part. Sorry, 45 times minimum D and S. I'm trying to write that in a way which is more manageable for us to manipulate. So I argue that this one I can write as 45 times D times the demand minus 45 times the max of 0 and the D minus S. Depending upon which one is larger, right? That's what you have.
That doesn't seem better.
Doesn't seem better?
No.
Well, at least you got something close to this.
Okay.
Right? It's not symmetric, of course, but you get something out there. Now, the next thing I'm going to argue is that here, this one purely depends on the demand. It has nothing to do with our decision variable. Our decision variable is what is how much what we order, right? So this one has nothing to do with what we order. That's clear, right? So I can drop it. As far as optimization is concerned, this is going to be a quantity. You don't have to concern. The optimal solution does not depend on this. Is that okay?
Huh.
Well, because this is the Q. If I put a constant 45 there, you will see that. But anyway, this one has nothing to do with what you order. Has no decision variable involved in there, so I can drop it. So I'm simply going to drop that to look at the rest of the cost function. Or for the moment, is the profit. Well, the profit and the cost are really negative. You know, if you maximize the profit, it's like you minimize the negative of the cost, right? So you can write down the corresponding cost. So here, if we look at what we would call relevant profit, it's a relevant profit because, as we said, no decision variable in this term, so I can drop it. So it becomes minus 45 times, so here it's minimum, sorry, maximum. D minus S, and minus 20S, then plus 9 max 0 S minus Well, we know one thing is it's nonlinear, but we managed to formulate the problem so we can actually put our hands on it and we can solve it. So at this point, there is no solution yet, but we just formulated that problem. So typically, for the one-stage stochastic inventory model, always involves something like this. You formulated that in that way. Okay, so if you look at that, what do you have? In this problem, we don't have a shortage, I guess. We have a sort of a salvage. We have the holding cost. We have then the regular order cost and things like that. But we also have a random variable built in. Now the question is, how do we handle this kind of problem? Now that's our objective in what follows. That's what I'm going to do next to solve the problem. So in order to do that, I'm going to depart from this model somewhat. Just write down a simple, even simpler problem and work on that first with you. And then we'll see how we solve that. So because it's a one period, so we have a single period. So those are the basic assumptions. Secondly, D is a random variable. The demand is a random variable. Well, whenever you have a random variable, then you have a distribution associated with that. You can think about how you solve that. Now, as I said, I'm going to start with a very simple example. So I will assume no initial inventory. If you put in initial inventory, it's also okay, but for simplicity, no initial inventory. We can handle initial inventory. Once you know the concept, that one just easily done. Okay, so we need some decision variables, right? Decision variable. Well, in this example, I put S as a decision variable. Here, I'm simply going to use our old friend, like Y, because we want to differentiation to do something like that. And also I want to distinguish this with this particular example, so it looks like different. And then we have the following sort of quantities involved. Let's put those in. The objective. Now instead of maximize profit, we are going to minimize cost. All right, so we have some rate or a sort of constant given. This is the unit cost for purchasing so this C in the previous case is like how much you order per bicycle, right? And then you have the holding cost. Holding cost per unit. All right, so it's the rate we are interested in. Now, finally, we also have the P. Like we did in the deterministic case, this is the shortage cost. Per unit of unfilled demand, right? So you for each demand, for each unit unfilled, you have a shortage cost with that. So the amount sold it's always you buy something and you sell that and then you try to solve the problem. So we use the the amount sold. This is exactly the same as in the previous case. It's this, it's the minimum of D and your decision variable, how much or how many units you order. Now, that one is equal to D if what D is less than 1 and equal to 1 if D is greater than or equal to 1. Well, the greater than or equal to, there is a point, but that point is not so essential. You can put in either way. Right? Okay, so now with this set, you can write down the cost function. If I write it here, I hope you can still go from that side, right? So the cost function involves two things. One thing is the demand variable. The other one is the decision variable, y. So to begin with, there's quantity like, how much you order, right? So the ordering quantity would be C times y. How much you pay. And after that, you will have the shortage cost and the holding cost. Basically, those are the only two parts in this simple example. So for the shortage cost, you have the unit shortage cost per unit is P. So you have the P multiplied by max of 0 because you are unfulfilled the demand. So here, of course, is the D minus Y, right? There is a possibility you don't have a shortage. That is, it's equal to 0, so then this part will disappear. But in general, we'll involve that part. There is also a holding cost part. The holding cost part is that times the max of 0, y minus D. So holding cost means you order something more than its demand. So of course it's a y minus D. So if you look at our previous example, that fits into the category like this. But now I'm doing this sort of like a general setup. However, I changed the decision variable from S to Y just so as to distinguish that from the last problem. So how do I do the optimization problem? Now see, if I think about it, there is randomness involved. So it's hard to say how to minimize this one because the thing fluctuates, right? What would be a natural thing to do if you have the randomness involved?
Treat it as cases.
Treat it as cases, or how about take the average of that, or expectation? So, for example, say I don't know if you walk into a mutual fund office, what would the person grade you ask you? If they ask you a question, what would he ask you? Of course, how much money you want to invest, right? And the first thing is, for example, you are trying to do an investment in 1 year. He would ask you, what is your expected value or expectation in return in a year, right? That's one thing. The other thing would be, what would be the sort of volatility or variation you can accept. Some people do not accept any variation. They want to have a true return. Then you don't want to go to a mutual fund company. You want to do the CD. Yeah. So what we are doing is we are going to knock out the randomness from here. In order to do that, we'll just take the expected value of this guy. There is no randomness involved in this decision variable. So now after you take the expectation, it will be a truly function of y only. So we call that function y. The reason C, it's a cost function, okay? So if you don't like to use C all the time, you can put a tilde here, if that's what you prefer, okay? So when I take the expectation, the first quantity is a constant, so that's not depending on the probability, so I can just write that as this. Now, for this part, I have the D involved, so I have to do something about it. So, so how do I take the expected value of this? Well, it depends on if you are working with discrete or continuous random variable. Last time we mentioned that continuous random variable means the distribution function is continuous. But if you think about some random variables taking values in minus point, those are discrete random variables, right? So I can rewrite that. I can introduce the probability here. So this one, how much? Well, I can write this in two parts. The first part, if I look at this part, I can write this one instead of the random variable, I'm going to replace by its value. So D, take the value D. Okay, so I'm writing this as D minus 1. Then I have to weigh this by the corresponding probability, right? So the probability, now I'm treating discrete random variable for the moment. In a minute, I'll write down the corresponding continuous one. So this one is the probability function of the random variable D. And here, this is basically the value of, say, D equal to D, right? So you are taking the value as D, but here is the corresponding probability, right? That's how the expectation is defined. I'll do it in a second. So here I have a random variable X. Let's better do the expected value of this. Suppose it's discrete random variable, then what I have the value of this multiplied by the probability of this, and the summing over all the possible X, right? So here, if you think about the possible D, actually you are not starting from anywhere else. You are starting from Y. Because if the thing is less than Y, it gets 0, right? So you go to infinity.
Is that a little p over there than like a big P?
Which one?
The one, is that one little?
This one is a little. This one is the shortage cost.
Oh, okay.
So unfortunately, that's people always use that as shortage cost. I'm using the same, But this is the big capital P.
Gotcha.
That's the probability. Whereas this one is the shortage cost unit value. So that's that part. Likewise, if you do this part, you'll have H multiplied by. This time you are summing up D, but you cannot go beyond Y, right? So it will be anywhere up to Y. So you may just, as well, because of the discrete random variable, you may just start from 0 to Y minus 1. Because started from Y, you are taking from this value. So that's the difference of continuous random variable and the discrete random variable. Continuous random variable, you have to worry about the point. Discrete random variable, you have to worry about. For continuous, you don't have to. All right. So here would be Y minus D multiplied by probability of D equal to. Right. So that's the problem set up. Now from this point on, you can do your calculus to find the optimal solution. But rather than do this problem, let me do the continuous version first. Suppose the random variable, the demand is discrete random variable, like binomial, geometric, or some others. Those are not so popular, but anyway, you assume that to be discrete. Now, for continuous, if D is a continuous random variable with a distribution function f, all right? So, and the density, what I use for density, I think a distribution function and PDF, I used phi because f is reserved for something else. So now, let's write down the corresponding Cy in this case. Now, I think intuitively it should be very clear. So here, the first term, no change, right? It's a decision variable proportional to the constant, per unit order quantity. Now, the next one, we have to replace this summation by what? Integral. And so instead of summing from y to infinity, you are doing the integration from y to infinity. And well, the constant, the little p here, let's recall that's the shortage per unit cost. And then you multiply this by
P minus y.
yeah, so let's use, instead of d, let's use x minus 1. The density function is phi of x dx, right? So that's for that part. So here we assume the density function exists. And then you have also another part. This part is the whole impulse part from 0 to y. And you have 1 minus x, phi of x dx, the same density